Chapter 6, Continuous Probability Distributions. So Chapter 5 dealt with probability distributions arising from discrete random variables. So remember, discrete random variables are usually counting objects in a category. So mostly that chapter focused on the binomial experiment. So there are many other experiments from discrete random variables that exist but that are not covered in this book. So again, it's just one intro course to statistics, but the most common discrete random variable we have is a binomial experiment, where we're just counting the number of objects that are in some category of interest out of the n objects that we sampled. Well, now in Chapter 6, this is going to deal with probability distributions that arise from continuous random variables. So keeping in mind again that continuous random variables are usually measuring things. So as we start looking at things like time and distance and volume and temperatures and heights and lengths and so on. So the focus of this chapter is a distribution known as the normal distribution. So again, realize that there are many other continuous distributions that exist. A few others are going to be examined in future chapters when we talk about things called sampling distributions. But again, the most common continuous distribution is the normal distribution. So again, in this intro course, it's the one that we will focus on here. But to get us started and to understand how we're going to be looking at probabilities slightly differently for continuous random variables than we did for discrete, we're going to start by just looking at a simple distribution called the uniform distribution, because it has a shape that, as we're looking at things with area that are going to correspond to probabilities, that we already have the math knowledge of how to compute areas for these types of regions. So let's say you have a situation where the probability is always the same. So a uniform distribution. So an example would be waiting for a commuter train. So the commuter trains on the blue and green lines for the Regional Transit Authority in Cleveland, Ohio, have a waiting time during peak hours of 10 minutes. So if you're waiting for a train, you have anywhere from 0 minutes to 10 minutes to wait, and we're going to assume that that has a uniform distribution over that interval of times. Okay, so the graph of that is given here in figure 6.1.1. So again, we're looking at times. So again, this is on a continuous scale. So again, there's ticky marks down here on the axis for 0, 1, 2, 3, and so on. But again, we don't count time, so it's not like it can only be 0 minutes or 1 minute or 2 minutes, but any value in between these is possible as well. Okay, now as we record time, as we're looking at like our cell phone or a watch or something, you might have a clock that only gets things down to the nearest minute or the nearest second, but time can get broken up into much smaller parts. So we just don't need to know time to that degree, as we're just planning our day and so on. And so like our cell phones just give us the hour, the minute, and the seconds. So suppose you want to know the probability that you will have to wait between 5 and 10 minutes for the next train. So we're going to look at this probability graphically for these continuous random variables. Okay. So here we're going to start with the uniform distribution that we have from 0 to 10, and we want the probability of getting an x between 5 and 10. Okay, so that's what this shaded region here represents. So we've got between 5 and 10, all of that region under our uniform distribution curve shaded in. So how would you find this probability? Well, calculus tells us that the probability is the area under the curve, between the curve and our x-axis here. So notice that the shape of the shaded area is a rectangle. So it's something that we actually know how to find the area for. And so the area of this rectangle, like any rectangle, is base times height. Okay, well, the base of this rectangle, okay, so the length here, we would take 10 minus 5. So the base, that length is 5 units. And then the height, so this height here, we go over here, we see that that height is 0.1. So we have a rectangle whose base is 5 and whose height is 0.1. And so the probability of being in this shaded region then is just going to be that base times the height, which gives us an answer of 0.5, which again, looking at our picture here, it should make sense that there's a 50% chance we would be in this interval because we've shaded half of the rectangle here. Okay, so here our random variable x is the waiting time during peak hours for a randomly selected commuter. So notice that the probability of getting an x value between and including the endpoints would also be 0.5. So the difference between these is one, we would have a rectangle that basically has dashed lines for sides. And now we're going to include those two endpoints. But these two areas are the same. Okay, well, if I could draw a rectangle that looked exactly the same height, they would be the same. So we're going to pretend those are the same area. So for a continuous random variable, whether or not the endpoints are included in the interval will not change the area of the shaded region. The only difference between these two rectangles is that one includes these little line segments on the ends and one does not, but a line segment has no area. A line segment has a height, but its base is 0, has no width at the bottom. So adding these two line segments adds no area to the rectangle. So again, this is for continuous random variables. So we need to be careful when we go to do the exam for this unit that we don't use things on discrete random variables that are only true for continuous random variables.